Hi and hello everyone. Welcome to our presentation, which is quantitative analysis of human blood serum using vibrational spectroscopy. And my name is Muhammad Naqib Syahmi bin Rosli, and then I am joined by my partner, which is Arash Jafni. Today we will explore how spectroscopy techniques like FTIR and Raman are transforming medical diagnostic through non-invasive analysis of blood serum. And we are going to the introduction first. Okay, vibrational spectroscopy. Vibrational spectroscopy, specifically infrared absorption and Raman spectroscopy, is used to analyze molecular vibrations in biological fluids like blood serum. These techniques are available because they are rapid and non-invasive, which makes them ideal for detecting disease markers and monitoring therapeutic drugs. And also, blood serum contains a wide range of components like proteins, lipids, and metabolites, which make it highly useful for diagnostic. It is easy to collect and cost-effective. True vibrational spectroscopy has been studied for decades. Recent advances now allow for quantitative analysis of both natural and introduced substance. Of the various methods, Raman spectroscopy stands out, especially for liquid phase analysis like blood serum. However, challenges such as spectral interference and sample variability can affect the accuracy. Solutions like filtration and spectral processing help overcome this issue. Ongoing research continues to push toward automation and clinical application, making this field even more promising. And for the next slide, let's take a closer look at the techniques involved. We are mainly talking about FTIR, ATR-FTIR, and Raman spectroscopy. For the first one, Fourier transform infrared spectroscopy, which is FTIR, identifies molecular vibrations and help detect functional groups in biomolecules. And for the second one, attenuated total reflection, FTIR, is a variation that improves spectral resolution and reduces the needs for complex sample preparation. And for the third one, Raman spectroscopy also detects molecular vibrations, but it is especially useful for liquid phase, making it excellent for blood serum analysis. And here's how the three techniques compare in terms of advantages. First, FTIR offers detailed identification of functional groups, and works well for solid or dried samples. And also, it is highly sensitive to polar bonds like OH and C double bond O. And for the second one, ATR-FTIR minimize sample preparation by allowing direct analysis on a crystal. It also avoids sample thickness limitation and improves spectral resolution. And for the third one, Raman spectroscopy is ideal for liquid phase analysis, requires little to no preparation, and is less affected by water absorption, which make it highly effective for analyzing blood serum. And for the limitation, we are going one by one because each technique also comes with its limitation. For the first one, FTIR. FTIR is highly sensitive to water, which limits its usefulness for aqueous samples like blood. It often requires drying the sample, which can alter its structure. It also has limited penetration depth. For the second one, ATR-FTIR. ATR-FTIR is surface sensitive and doesn't analyze deeper layers, and it can lose accuracy when the sample is too thick and needs careful contact with the ATR crystal. For the last one, Raman spectroscopy faces fluorescence interference, lower sensitivity for polar bonds compared to FTIR, and uses strong laser power which might degrade the sample. And next, blood serum contains both endogenous and exogenous constituents. Endogenous components include high molecular weight fraction like albumin, fibrinogen, and immunoglobulins. Imbalances here can indicate hydration issue, sepsis, or heart problems. And also, low molecular weight fraction such as glucose urea, and small metabolites. These are important for monitoring diabetes, kidney, and liver function. And for the next one, which is exogenous constituents, include viral load, used to assess infection severity and guide treatment. Therapeutic drugs level, helping personalized dosage based on metabolism.
Assalamualaikum. My name is Muhammad Arash Jafni bin Muhammad Sharizan, and I will go through the presentation for the next part. So, here is the experimental considerations. So there are three things that we need to consider in the experiment. So, first one is sample preparation, which is it includes blood serum collection and also filtration techniques. So, in blood serum collection, we will standardize collection methods to ensure consistency. And also, anticoagulants like heparin and EDTA can affect spectral results. So, for filtration techniques, centrifugal filtration separates high and low molecular weight fractions, and also it can improve quantitative accuracy for low molecular weight biomarkers. So for the second one, which is spectral processing, we need to consider both baseline correction and also signal enhancement. So for baseline correction, we need to remove unwanted spectral variations, and these methods includes rubber band correction and also vector normalization. So for signal enhancement, the first one is extended multiplication signal correction, which is EMSC, can improve spectral clarity, and it also helps eliminate water in interference in Raman spectroscopy. And the third one that we need to consider in the experiments is data analysis techniques. So the first one is partial least square regressions, which also called as PLSR. So it is establish a model linking spectral data to analyze concentrations. It is also used for predicting biomarker levels in clinical diagnostics. Next one is cross-validation methods. It is to ensure model accuracy by testing on randomized data subsets, and also measures rates, and also it is measure error rates. For example, RMS-ECV and also RMS-EP for validation. Alright, moving on to the next part, which is clinical applications. So vibrational spectroscopy is already proving its usefulness in several clinical areas. For example, the first one, disease diagnostics. It helps identify biomarkers for metabolic disease, cardiovascular condition, and even cancer at early stages. Next one, therapeutic drug monitoring, which is also called as TDM. It is an accurate drug level measurement which help tailor dose to each patient. The third one is viral load quantification. Spectroscopy can monitor infections quickly and non-invasively. The fourth one, for future prospects, the automation and real-time analysis are on the horizon. These techniques could become part of everyday clinical practice. It helps doctors respond faster and more effectively. Alright, moving on to the challenges and solutions. While promising, vibrational spectroscopy still faces a few key challenges. For example, first, sample inhomogeneity. This is because serum composition varies, so the results can be inconsistent. So the solutions for this, we use filtration to improve uniformity. The next one, spectral interference. Water and fluorescence can distort the spectra, so we use baseline correction and also signal enhancement techniques in order to remove these unwanted signals. Next one, sensitivity and quantifications issues. It is difficult to detect low concentration markers due to dominant proteins, so we use fractionation to help isolate and detect them more easily. And last but not least, clinical translation. These methods aren't fully used in hospital yet, but automation and real-time analysis are helping making them possible. Moving on to future prospects. So what's coming next? The first one, automation and real-time analysis. Right now, manual steps slow things down, which automation would streamline sample processing and analysis. Next one, integration and diagnostic. Clinical protocols and validation studies are needed to bring spectroscopy into hospitals and labs as a routine tool. Advancement in data processing. Spectral data is complex, so machine learning will help interpret it more accurately and efficiently. Last but not least, expansion of application. Current methods targets a small number of biomarkers, so broader studies could unlock many more use in diagnostic and therapy monitoring. Alright, so to summarize things up, vibrational spectroscopy, especially Raman, offers a fast and non-invasive way to detect and quantify blood serum components, while challenges remain like sample variability and data complexity. Solutions like filtration, spectral processing, and machine learning are making the process more accurate and scalable. As automation and clinical adoption progress, we believe vibrational spectroscopy will become a standard tool in diagnostic and also personalized medicine. Alright. Right, so that's all from us. Thank you for lending us your time and stay with us until the end of presentation. Thank you very much.